Hello everyone, welcome to Module 3 for CNEAS 7103 at the University of Utah. Today we're going to be talking about models of error and different sampling distributions. And in particular, we're going to focus on why we like the sum of squared errors as an estimator and why we like the mean as an estimate, given a number of different properties of estimators. So first, it's important to remember that we're usually going to be trying to make inferences about a population from a sample that we've drawn, right? So values that we observed in our sample are going to be estimates of the true values in the populations. And the technical term for this is an estimand, right? An estimate is something we derive from the data that we have, and we hope that the estimate is a good approximation of the estimand, right? If they line up, it's a good estimator. If they're off, our estimate is probably inaccurate. And usually our estimate is not going to be accurate, but we hope it's a reasonable approximation. And in order to do that, we're going to look at different functions that we use to obtain an estimate. So those functions are called the estimator. So these are probably new terms, or at least we're using them probably in a more technical sense than you used them before. But we want to employ functions known as estimators, right, that will give us a representative value, known as an estimate, for the quantity of interest, which is the estimand. So that is, in our sample, we want to use the estimator that will give us the best estimate of the true value out in the population, right? We're going to fit a parameter. We're going to get that value B that we think is the best representation of beta, because beta is not known, right? In reality, we can't actually see what beta is because we're probably never going to sample the whole population. But we want to make sure that we are using mathematical tools that will give us a reasonable approximation of beta. And we can show this in a couple different ways. We can show it mathematically, but we can also show it empirically through simulations, which is what we'll do a lot in the lab. And the simulations are nice because it allows us to control what beta actually is. We can actually see what the underlying value is, and then we can see how our estimates of that value change. And when we're talking about comparing different methods of estimation, there are a few key desirable properties of estimators. In particular, we're going to focus on three desirable properties of estimators. One, we want estimators to be unbiased, efficient, and consistent. So unbiased means that our estimator is probably going to overestimate the estimand, and sometimes it's going to underestimate the estimand. So sometimes we'll be high, sometimes we'll be low. Any individual estimate is probably not accurate, but on average, they will be accurate because 50% of the time will be above what we're will be above the estimand. 50% of the time will be below the estimand by approximately the same degree. So unbiasedness is a very desirable property. Any individual estimate probably isn't accurate, but on average, we will be accurate. Second, we like our estimators to be efficient. Given that two estimators are unbiased, we're going to prefer the one that has a smaller variance or spread around the estimand. Right, so again, think about it being unbiased. If we have lots of different estimates, some of them are going to be above the estimand, some of them are going to be below the estimand. So how much they spread out is a measure of their efficiency. If our estimates tend to vary wildly, they're not very efficient. If our estimates all tend to cluster together, that's an efficient estimator. So we will generally prefer an estimator that is more efficient, assuming that it's also unbiased. Third, we also want estimators that are consistent. And consistency means that as the sample size increases, the estimator produces a better and better approximation of the estimand. So in a sample, for instance, with 10 people, we don't think that the mean is going to be a particularly accurate reflection of the population mean. Because with a sample of 10, I'm going to get one person who's an outlier, two people who are an outlier. It's going to get pulled in a lot of different directions. Now, if I take a sample of 10,000, we think that's probably going to be a much better representation. And indeed, the mean follows this pattern. As your sample size increases, the mean asymptotically approaches the population mean, right? So it's going to get closer and closer to being a good approximation of that mean as the sample size increases. And we can actually illustrate these properties by sampling from a few different distributions. So we're going to sample from two different distributions of errors, right? We're going to assume that we have error scores that are centered around 0, and then we're going to have some negative errors and some positive errors. And we're going to take two different populations of errors. So I have 100,000 errors here that follow either a normal distribution, right, where they're sort of clustered around the mean, but they fan out in either direction, or I have a uniform distribution of errors, where they are still centered around the mean of 0, but it's the probability of a certain error is flat. It is level across the population, right? I'm just as likely to have an error of -4 as I am +4. So here we have a uniform distribution. Here we have a standard normal distribution of errors. And I've written some R code, and we'll go over this simulation in the lab, to draw samples from each of these populations. So just to show you what this might look like, here we're taking different samples. So I've got 2 samples from our normal population and 2 samples from our uniform population. And you can see that I have 10 observations in each sample. And you can see here I've got a couple scores. I have one of negative almost -2. I've got 3 that are quite close to 0, right? And then I have some positive scores. In our second sample, we get a slightly different distribution. I have a few negative scores here. I've got 2 that are close to 1, right? And then a few more positive scores. Similarly, with the uniform distribution, when I take a sample, each sample is different, right? So I have more extreme values when I'm sampling from the uniform population, right? You can see over here, I didn't tend to get -4s or +4s, but here -4s and +4s are pretty common because again, in the population, there's an equal probability of drawing those at random. So here I'm simulating random samples. So this is what it would be like if we randomly sampled a population. Now, when we do this in an experiment, we probably draw 1, maybe 2 samples from the population, right? We were going to run one experiment, maybe we run a replication of that experiment. With simulations, though, it's quick and easy to do this, for instance, 10,000 times. So let's look at what happens when I sample 10,000 times from each of these 2 populations. And what we're interested in is what's going to be a better estimate of the mean in the population, right? So I want to know if I take the mean of this sample, is it going to be a good approximation of the population mean? And if I calculate the standard deviation of this sample, is it going to be a good approximation of the population standard deviation? So in the last module, we talked about the mean versus the median as 2 different estimators, and the sum of squared errors versus the sum of absolute errors as we talked about the mean and the median as 2 different estimates, and the sum of squared errors and the sum of absolute errors as 2 different estimators, right, or methods of estimation. So we're going to compare these things with respect to their unbiasedness, their consistency, and their efficiency. And we have 2 different populations, right? I have my normal population and I have my uniform population. Here we have the mean of sample means, right? So if I took all 10,000 samples of 10 people, I averaged all of their means together, I got -0.007. The standard deviation then of those means was 0.32. So they varied around the mean by 0.32. Coming from the uniform population, the mean of means was -0.025, right? So again, I took 10,000 sample means, I took the mean of all those means, and it's very close to what the population mean was. The true population mean was 0, right? So this is pretty close. And then the standard deviation of those means is 0.722. So you can see, comparing these 2 parent populations, our sample means are more tightly grouped when we're coming from a normal distribution, and they're more spread out when we're coming from that uniform distribution, which makes sense because, as we said, outliers are going to be more common when we're sampling from that uniform population. Or sorry, not necessarily outliers, but extreme values are going to be more common when we're sampling from that uniform population. We're more likely to get a 4 or a -4 in this case compared to this case. And now let's look at the medians. So if I took the mean of all the medians, right, it's still a pretty good approximation of the underlying mean, right? And if I took for the uniform population, right, it's also still not terrible, right? This is on average doing pretty well. Both of these estimators seem pretty unbiased, right? They're both centering around 0. Now, if I took the standard deviation of the medians, though, you could see that here this is 0.37. So when we're sampling from the normal population, the distribution of medians, right, is a little bit wider than the distribution of sample means. And now if we look at sampling from the uniform population, right, again, it's unbiased, but if we look at the spread in those sample medians, it's quite a bit wider than the distribution of sample means. So here we can see that both the mean and the median are unbiased, right? If we look at this value compared to this value, or this value compared to this value, these don't seem to be particularly biased as estimators. But now if we look at their efficiency, right, and we compare these standard deviations, the standard deviation of sample means is lower in both populations compared to the standard deviation of the medians. So it seems to be a more efficient estimator. Well, what about consistency? Again, that's a question about how the sample size has an effect on the efficiency of estimation. So let's change from samples of 10 to samples of 50. So again, we're taking 10,000 random samples, but now rather than 10 people per sample, we have 50 people per sample. And we're drawing from a normal population or the uniform population, right? And now we're going to look at the mean, the distribution of sample means. So we're going to look at the mean of means and the standard deviation of means. And we can see that the mean of means is generally pretty good, right? We're quite close to 0. And the standard deviation of means gets smaller, right? So this is a consistent estimator. The spread of our sample means is getting tighter as we have a bigger sample size. And that's true whether it's a normal population or a uniform population. The spread of the uniform population is still bigger, but the mean is still a consistent estimator. Because it is going down as we go from 10 observations to 50 observations. Now, let's look at how the median is performing. We can see, okay, again, the median is relatively unbiased when we take these samples of 50, and the standard deviation of the medians is going down as we go from 10 to 50 observations. So the median is also a consistent estimator. So in summarizing the comparison across all of these different simulations, we can see that both the mean and the median are unbiased and consistent estimators. However, in the examples that we looked at, sampling from a normal distribution and sampling from a uniform distribution, the mean tends to be a more efficient estimator than the median. And this is true for a lot of different distributions as well. But in general, this is why we're going to prefer the mean and the sum of squared errors, because it leads to more efficient estimation than choosing the median and the sum of absolute errors. There are some other unique mathematical properties of squares that make it quite important, especially when we start talking about an analysis of variance and some other sorts of distributions. But a very important reason why we're going to choose the sum of squared errors and the mean as an estimate is because it's a more efficient method of estimation than the median. Now, this conclusion will depend on the underlying distribution, right? As we saw, the efficiency of this depends on whether we were sampling from a normal distribution or a uniform distribution. And in general, the mean was performing much better in the normal distribution compared to the uniform distribution. And there are many possible distributions of errors that we might want to assume, but there are good reasons for choosing the normal distribution. And in chapter 3 of the book, they describe this in detail, and we'll review some of those points here. We can see that empirical data, so we can sample lots of different things, whether we're sampling, people's perceptions of enjoyment and calm in the outdoors, whether we're sampling people's heart rate at rest versus exercise. Lots of different empirical examples that you can choose that will show approximately normal distributions are very common. And part of the reason for this is that linear combinations of variables, even non-normal variables, lead to approximately normal distributions. And we'll run some simulations in lab to show that this is the case. But even if I take 3 different uniform variables and I add them all together, the resulting sum is going to be approximately normally distributed. And the reason for this is if I have 3 random variables being combined, it's unlikely that I'll get 3 extremely large positive values or 3 extremely large negative values for all 3 of those variables. More likely, I'll get some mix of positives and negatives that cancel each other out. So most of the scores are going to cluster in the center with fewer and fewer extreme outliers. And you can show this for lots of different combinations of variables, but this is part of what makes the normal distribution so cool, or at least the approximately normal distribution so cool, is that when you're combining lots of different factors, assuming they are independent of each other, whether they're normally distributed, uniformly distributed, skewed, otherwise, anytime you're adding lots of different variables together, if they're independent, the chances of getting all positives or all negatives is very small, and that means you're going to get most scores that cluster together somewhere near the mean. And finally, the central limit theorem, as we'll show in detail in the labs, shows us that sample means, even if we're drawing these samples from non-normal distributions, will be approximately normal. And if the sample size is large enough, they will actually be very close to the normal distribution. So whether we're sampling from skewed distributions or uniform distributions, if we're sampling, the distribution of sample means is going to be approximately normal, and it's going to be more normal the larger our samples are. And finally, as they discuss in the textbook, even when non-normal, many distributions can be transformed to become approximately normal, right? So skewed distributions, for instance, if they're positively skewed, right, if we have some outlying scores in the positive direction, they could be square root transformed or log transformed, and now we've reduced that skewness and made a distribution that is more approximately normal. So normal distributions are going to do a lot of work for us when we assume a normal distribution of errors, and that's going to allow us to make some very specific, very quantitative statements about the likelihood of observing events in our data.